Okay, so hello everyone, and welcome to the third lecture of Subhash Khot, where, as far as I understand, we finally get to unique games. So, Subhash, please.
Oh, okay. So I will start now. Oh. All right. So far we in the first lecture we saw hardness result for this edge disjoint paths, which is the pre-PCP theorem. Then the second lecture, this Asta's result for the three-lin problem, which is the post-PCP theorem. And now we'll see optimal hardness result for max cut. But here we do have to use unproven hypothesis, which is the Uni-Games conjecture. So the max cut problem. So of course, you have the algorithmic side and then the hardness side. From the algorithmic side, we have the Bowman-Williamson's algorithm based on semi-definite programming. And then it turned out that under the Uni-Games conjecture, this algorithm is optimal. And that's the hardness result we'll see. And here we are going to need a Fourier analytic theorem called majority is stablest. Now, the algorithmic side is not the focus of this talk like per se, but it will be good to quickly take a look at the algorithm, which was supposed to be the reading assignment. So I'm going to be really quick. So this is all just basic material on what semi-definite programming is. So I'm going to skip that. So the max cut problem, given a graph, you want to find a cut, partition of the graph into two sets, so as to maximize the number of edges which is cut, right? And you can formulate it as quadratic integer program. To ith vertex, you assign a variable xi, which is supposed to be plus minus 1. And then the goal is to find the maximum of this expression, 1 minus xi xj over 2 over all edges I comma j, right? And this is an NP-hard problem, but then we can take what's called the semi-definite programming relaxation, where these variables xi's, instead of restricting them to be plus or minus 1, you allow them to be unit vectors in arbitrarily high dimensions. Okay, and then that leads to an approximation algorithm within factor alpha sub GW, which is a number which is about 0.878. So this is the actual problem, maximize summation 1 minus xi xj over 2. And then this is a semi-definite programming relaxation, which is maximize summation 1 minus vi dot vj over 2, right? So this is the standard dot product of vectors over all unit vectors, vi's. Okay, and this turns out can be solved in polynomial time. And so this value, which is the value of the SDP relaxation, it's a relaxation, so it's clearly at least the optimum. But then it turns out it's also possible to lose a factor of this about 0.878, and then from the SDP solution actually find an integral solution, or the actual cut in the graph, so to speak, by losing a factor which is right up to this Bowman-Williamson constant. And this is done by a so-called rounding method. And here the rounding method is these vectors are points on unit sphere. So pass a random hyperplane through the origin, and then that cuts the sphere into two parts, and hence also these points vi's, and therefore also the vertices of the graph into two parts. Okay, and then one shows that this does achieve approximation guarantee of this factor alpha sub GW. And this, at least in hindsight, this is actually quite straightforward. You just show that this holds for every edge. Okay, so fix any edge, let's say ij, and let theta equals theta sub ij be the angle between vi and vj in the SDP solution. Okay, and now you just compare what this edge contributes to the SDP objective and how much it contributes when you actually round it. Okay, and then the approximation ratio is simply the worst case ratio between the two. Okay, so if the angle is theta, you passed a random hyperplane, so you did manage to cut the edge with probability theta over pi. On the other hand, in the SDP objective, it's 1 minus vi vj over 2, which is 1 minus cos theta over 2. Okay, and then in the worst case, you will lose a factor of which is the ratio between these theta over pi and 1 minus cos theta over 2. So take the worst case or the minimum possible value of this ratio. It turns out it's achieved at about critical angle theta sub c, which is about 117 degrees, and the minimum is about 0.878.
Sorry, Subhash, there is a question in the chat which I don't quite understand, so I would ask the participant
right.
Hello. So can this probability be 0, or like how to handle the 0 probability case like this? You take the theta, like the probability that the unit vector are like which like lands in the projection on the span of these 2 unit vectors, and that basically governs whether this.
Right. So that's a major zero event, so to speak. So that will essentially never arise. If you think of it in the continuous domain.
Okay.
Right. Okay. So yeah. So this is the this is how the Gomans-Williamson constant is defined. Okay. Right. So let's move on to the actual hardness result. Right. So we want to show that you can prove a matching hardness result. Okay. And then this is via assuming the unique games conjecture. So we'll get to the unique games conjecture, the formal statement later. But for now, assume that the unique game as a computational problem is actually same as the label cover problem that we came across before. It's in fact a more specialized version of label cover. And just like label cover, right, similar to label cover, but here we need to make a conjecture. That is NP hard to tell whether the optimum is close to 1 or it's at most delta, some tiny. Okay. One distinction from the standard label cover is that in the completeness case, we can only hope to have the optimum which is close to 1, but not quite exactly 1. So it's imperfect completeness, and that's necessary actually. Okay. And then we have this reduction from the unique games or the label cover problem L to the instance of max cut, which is just a graph. And the reduction has the property that depending on whether the optimum of the unique game or label cover is close to 1 or tiny, the graph either has a large cut or all cuts are small. Okay, where large means 1 minus cos theta sub c over 2, and the small means at most theta sub c over pi. And when we do this reduction, we choose a specific value of this angle theta sub c, which is same as the critical angle theta sub c, which achieves this Gomans-Williamson minimum, right, in this constant theta sub c, if you express in degrees, about 117 degrees. So you see that now if you assume the unique games conjecture, it's NP hard to distinguish between the two cases on left-hand side, and therefore it will be NP hard to distinguish whether there is a large cut or no large cut. And the ratio will be precisely equal to the ratio between these two, which is exactly the Gomans-Williamson constant, right? And therefore you get a matching hardness result. And of course, you have to allow for some small additive eta, which is arbitrarily small. Okay, so this is how so I'm just giving you how what the reduction will achieve. But it turns out to actually design this reduction and then to show that it works, we have to do some use some tools from Boolean function analysis, and in particular here we need to study what is called noise stability of Boolean functions. So let me spend some time on this notion, noise stability. So fix a number rho, a positive number. Think of it as being very close to 1. So it's 1 minus 2 epsilon for some tiny epsilon. And now I pick two inputs, x, from the standard n-dimensional Boolean hypercube. So you can either think of this as a pair xy which is correlated, or you can think of it as first picking x and then y being the noisy version of x. And these are simply equivalent. So let's imagine that we first picked input x, and then you could pick y in one out of two equivalent ways. Perhaps more natural is to think of y as a noisy version of x. So for each coordinate, yi is xi with probability 1 minus epsilon, and with probability epsilon, you flip that coordinate. Okay, or you can think of it as keep yi as same as xi with probability rho, and choose to be uniformly random plus minus 1 with remaining probability 1 minus rho. And you can convince yourself at home that these two are the same when I set rho equals 1 minus 2 epsilon. Okay, So you can think of either of the two ways. And what we want to study is the so-called noise stability of functions. So given a Boolean function f, the stability is stability of the function f with respect to the parameter rho, which is really the correlation or noise parameter, is the probability that if I pick x and the noisy version of x, which is y, the probability that f of x is equal to f of y, meaning the function is stable under this noise. Okay, so this is the notion of stability of a function. Turns out you can express stability of a function in terms of the Fourier coefficients of the function. And here is the precise expression for stability. We are really not going to use it because we are going to skip most of the proofs. So let me not skip this part. But one thing to keep in mind is, since the stability has an expression in terms of Fourier coefficients, now it makes sense even to talk about it, even if the function was not Boolean valued, but actually real valued. And let's say the function, the values are bounded between -1, 1, but it could be real values. Yeah, and then the stability, according to this formula, it would still make sense. Okay, so that's the definition of stability. And here is a question you could ask yourself: which function, which Boolean function maximizes, is the most noise stable? Okay, but of course, if the function is simply constant, meaning if it always takes the value +1, it clearly will be most stable because you will always have f of x equals f of y. So you have to make the problem non-trivial, and you make it non-trivial by requiring the function to be balanced. Say expected value of f is 0, meaning the function takes +1 half of the times and -1 half of the times as values. Okay? So now it's a more interesting question: which is a function which is balanced which is maximally stable? Now, turns out again the answer is quite easy to come up with. It's the dictatorship function, the function which depends on exactly one coordinate. And if you want, here is a simple proof, but let me skip that. So dictatorship functions are very stable, and in fact, stability of a dictatorship function is 1 minus epsilon, because there is only one coordinate which is relevant, and with probability epsilon you flip the coordinate. But with probability 1 minus epsilon, that coordinate stays the same, and therefore the value of the function remains the same. Okay, so therefore the stability is 1 minus epsilon. Now, if the function depends on, let's say, k variables, then you can certainly say that the stability is at least 1 minus k epsilon, because just by union bound, with probability 1 minus k epsilon, those k variables will just stay intact, right? And the value of the function will be preserved. And if you take but if it's a function on k bits, but it's a parity, then it's easy to show. In fact, here is a calculation that the stability rapidly drops, and let's even say it becomes a parity on all n coordinates, and n is thought of as unbounded. Then the stability essentially drops to 1/2, right? Because imagine if you have very large number of bits, and if each of them is flipped with probability epsilon, and then you take the XOR, which is the parity, then you will have flip or not flip with probability half essentially. So it drops all the way up to half for a parity function on a large number of coordinates. So here is a question. So of course, right? So the general intuition is that if the function depends on more and more variables, its stability keeps dropping. Okay. So here is a question: if the function depends on many variables, what's the highest stability we can still hope for? Okay, and the reason we want to do this is a function which depends on many variables is thought of as being far from dictator. Okay, and if you recall what we were trying to do in the last lecture, we were somehow trying to distinguish between functions which are dictators versus functions which are far from dictators. Okay, and it's the same game again. We somehow want to distinguish between functions which are dictators and those which are far from dictators. So that's the reason. Now, a priori, I mean, if I had to guess, like within like half a minute, if the function depends on lots of variables, then I would guess that maybe the stability has to drop all the way up to half, right? Which would be the parity function. But actually not quite. Turns out there is this function, let's say that the majority function. So majority function is, it looks at all the n bits, and if the pluses are in the majority, the value of the function is +1. If -1s are in the majority, the value is -1. Okay, so it's a balanced function. Yeah, you can think of n as odd if you like. And it turns out that the stability of the majority function is, well, in the case when rho is really close to 1, say 1 minus 2 epsilon, the stability is actually very close to 1 as well. It's 1 minus theta of square root epsilon. So these are all fairly easy exercises which you should do on the side. And there is even more precise formula for any rho as n tends to infinity. If you think of majority as on huge number of variables, then in the limit, it's actually, there is an exact formula, 1 minus 1 over pi cos inverse of rho. In particular, rho is positive, so cos inverse of rho is less than pi over 2. Okay, and therefore this number is larger than 1/2, right? So the stability actually stays strictly above 1/2, which is which is a nice observation. So majority is actually remarkably noise stable function. Right. So let's keep that observation aside for a minute, okay? And let's come back to this notion of or a definition. When do we want to consider a function as being far from being a dictatorship function? Okay. So if you go back to our last lecture, we did have some notion of whether a function resembles a dictator or not. Okay. And here we are going to introduce another notion. This will be a new notion. And which notion you really care about for, that really depends on what the notion is good for, depends on the application. And it just turns out that for the application for today, the notion that we will define now is the correct one. Okay, and this is a notion, it's also a well-studied notion. It's called influences of functions. So here is a formal definition. So you have a function f, it's a Boolean function. Then influence of a coordinate I is the probability that you pick a random input and flip the ith coordinate. And then what's the probability that the value of the function itself changes? Okay, that's called the influence of that coordinate. Okay, I mean, if you haven't seen this notion before, it takes some time to, to somehow internalize it, right? But I hope at least some of you took a look at the notes beforehand. So this is the notion of the influence, right? Influence of a coordinate. Turns out influence also has a formula in terms of the Fourier coefficients. So influence of the ith coordinate is sum of squares of Fourier coefficients containing that coordinate. Okay, but again, let's keep that aside. And turns out if you look at the majority function, all of its, if it's a dictatorship function or even a parity function, actually, all the influences are 1. That's easy to see because you flip a coordinate, the value of the function flips. On the other hand, for majority, all the influences are small. In fact, all of them are 1 over root n for a majority of n bits, and n is thought of as unbounded. So all these influences are thought of as negligible. So majority is a function whose all influences are negligible. And now this is our notion that if we say that a function is far from dictator if all influences are small, okay? Because if there was a coordinate with large influence, right, that would sort of resemble a dictator, right? Because dictatorship function does have that one particular coordinate whose influence is 1, the largest possible value, right? So having an influential coordinate is thought of as resembling a dictatorship function, okay? And therefore, a function is far from a dictatorship function if all influences are small. Okay? And this is why we really want to study functions whose all influences are small. Okay, so I hope that made sense. And here is the theorem, which is called the majority of stabilist theorem. The informal statement is here. Among all functions, which are balanced functions, of course, you have to include that condition to make the statement non-trivial. So among all balanced functions where all influences are small, it's really the majority function which is the most noise stable. Okay, so this is called the majority stabilist theorem. And here is the formal statement, but you can skip the formal statement for now. It just says that for any rho, there is a small enough constant delta such that any balanced function whose all influences are small, the stability is at most equal to the stability of the majority function. Right? So this 1 minus 1 over pi cos inverse rho, this is the stability of the majority function in the limit. Right? So the stability is at most the stability of the majority plus some arbitrarily small additive constant epsilon. So in this sense, majority is the most noise stable function among the functions whose all influences are low. Okay. And here is the intuitive reason why stability of majority is 1 minus 1 over pi cos inverse rho. So I will skip this. Okay, so to keep in mind, majority is the function which is most noise stable among functions where all influences are small. Okay. Okay. So now it turns out when we actually do the application to the MaxCut problem, what we need is something actually a little bit different, and in fact, in some sense, something which is even diametrically the opposite. Okay. So you need two variations on this theorem. So in the application, we need two variations. One variation, both are important. So the first variation is that you really need to work with negative correlations. So the correlation parameter rho is now actually close to -1 as opposed to being close to +1. So what this amounts to saying is that if you want to think of it as a noise, then you flip every coordinate essentially with probability 1. Okay, so that if your starting point x, the point y, it becomes almost antipodal of x. Okay, so it's an extremely high noise case. And if you think of in terms of the correlation, it makes the correlation close to -1. Okay, so that's one variant that you want to want. And the second variant you need is, instead of the influences directly, we have to work with what are called the low degree influences. And so for some parameter k, this is the instead of the influence of the ith coordinate, you want degree k influence of the ith coordinate. And here is a definition. So degree k influence is, so recall that just if it were just the influence, it would be sum of squares of Fourier coefficients containing that coordinate I. But this new influence, this new notion, this is called low degree influence or k degree influence. You only take sum of squares of Fourier coefficients which contain the coordinate I, but only those sets which are of size at most k. Okay. And why we need this notion is the following reason, that eventually what we want to do is, given a Boolean function, right, we want to somehow decode it. So given a Boolean function, we want to identify certain coordinates as being special, right? And that's a notion of decoding. We also used this in the last lecture. And here clearly we want to, as decoding, take coordinates which are influential. Okay. But when you do decoding, let's say even in coding theory, we always want what is called list decoding, meaning we want to make a list of all possible decoded coordinates, and the list better be bounded, because otherwise it's just meaningless. You could have just enlisted all coordinates, right? And that would not give you any information. So we always want list to be of bounded size. Okay. And this is why we need to consider these low degree influences. So the point is that yeah, so I'm going to use these notes just for one slide. Yeah, I hope, I don't know if you see this. Right. Okay, so I hope you see this. Yeah, and then the point is that if you use this in the degree k influences, then their total sum is at most k, and therefore if you took all coordinates, let's say I sub 0, whose degree k influence is at least delta, there are not more than k over delta of them, right? So you make a list of all those that have large influence, say at least delta, then the list stays bounded. It's at most k over delta. And this is simply because of the following calculation. If you sum up these influences, degree k influences, over all coordinates I, then by definition it will be sum over I, sum of squares of f hat s square over all sets S containing I, but those sets which are of size at most k. Well, it's a small issue that in the last lecture, my Fourier coefficients were called f hat of alpha, but now I'm calling them f hat of S for sets. It's just a change of notation. And then you can rearrange this sum. You can take the switch, right? You can first sum over all S of size at most k, f hat S square, and then each set will be counted as many times as its own size, right? So you have to multiply by size of S. But now the sum is over only sets of size at most k. So this whole thing is at most k times sum of squares of Fourier coefficients, which is 1. So it's at most k, right? So sum of all these guys is at most k. And therefore, if you, in the decoding, if you took all those which are at least delta, right, your list will be only of size k or delta. And this is the purpose of working with the so-called degree k influences. So let's go back to our right. Okay, and so we have to work with these two notions: negative correlations and low degree influences. Okay, so here is further emphasize what negative correlations mean. We let the correlation parameter to be essentially actually close to -1. But here now what happens is once you did this flip, right, the correlation went from being close to +1 to close to -1. The problem itself also flips. So now instead of maximizing the stability, turns out the question is to minimize the stability. Okay, I mean, just trust me on this, right? And now it turns out you can even drop the restriction on whether the function is balanced or not. Okay, even without that, the problem remains non-trivial. Okay, so now we want to minimize the stability. That's it. Okay, and here is the theorem, which we call theorem number 3, and this is really the theorem that we need towards the application. So let me do it closely. So fix correlation parameter rho, which will be close to -1. Then there is a small enough delta, large enough k, such that the following holds. And here it doesn't matter what this dependence is. The point is that the dependence is only on rho, not an epsilon, and not on the n, which is the dimension of the hypercube. So everything is independent of the dimension of the hypercube. That's what that really matters. And then the theorem is, give me any function. If all degree k influences are small, at most delta, then the stability is at least equal to the stability of majority minus epsilon. Okay, so, or in other words, if all influences are small, then it's the majority which minimizes the stability. Okay, and again to emphasize, we started with positive correlation and then the majority was stabilized, but now we switch to negative correlation and then the majority is unstabilized. Okay, so this is the theorem that we really need, theorem number 3. And the theorem number 1 and also theorem number 2, which I in fact even skipped. Turns out, and theorem 3, these all follow from the theorem number 1. Okay, so and then there was much of the notes they were about how theorem 3 follows from theorem 1. But at this point, you can forget everything and just take this theorem 3. This is what we really need. And if you want, you can open a side window and just so that you can stare at the statement and have the statement ready. All right. And now we will come back to the actual reduction. So the actual hardness result. Okay, so just to recall, we want to take the Unigame's conjecture, which is same as hardness of label cover on a very special case. So of course, I haven't defined what Unigame's conjecture is, which I will do. And then we build a dictatorship test, just like the last lecture. But here the dictatorship test will, or its analysis, it's basically same as the majority's unstabilized theorem. Again, majority is unstabilized under negative correlation. Okay, again to emphasize. Right. right? And then put the two things together, and we will get the optimal hardness result for max cut. Okay. And here again to recall the general scheme, right? So unique games is just a label cover problem L, which is guaranteed to be either highly satisfiable or highly unsatisfiable. The optimum is either close to 1 or very tiny. And then this reduction will have the property that depending on that, the graph that we construct will either have a cutoff size, large cut of size 1 minus rho over 2, or there is no cutoff size more than marginally more than 1 over pi cos inverse rho, right? And we are going to set this parameter rho as precisely rho is equal to cos of the theta of C, cos of the critical angle. And this is the same critical angle, right, which we came across before, which achieves this Bowman-Williamson ratio, about 117 degrees. So since this theta is 117 degrees, cos theta will be negative. That's the rho. That's why our correlation is negative. Okay. And then you get a hardness of approximation, which is the ratio between these two factors, right? 1 over pi cos inverse rho and 1 minus rho over 2, which is exactly the Bowman-Williamson ratio, up to this additive epsilon, which is arbitrarily small. Okay, so that's the result. Okay, so finally, okay, so before going to the actual unique games conjecture, let me describe what dictatorship test is. Actually, dictatorship test is basically same as this noise stability, or to be more precise, is actually noise unstability. So given a function f, right, we want to test whether it's a dictator. And the test is simply pick two inputs x and y. X is random, and then y is the noisy version of x, and accept if and only if f of x is different from f of y. Now, maybe I should have emphasized right in the beginning, why do we even care about this parameter called noise stability? Right, because we care about max cut. I think I should have emphasized this before, but let me emphasize it now. So if you consider the following graph, where the vertices are vertices of the hypercube, and then the edges of the graph are these pairs x and y, right, which occur in this test. Right, these are x and y, these are these correlated pairs. And then you accept if f of x is different from f of y. Now, if you think of the function, which is plus minus 1 valued, as a cut in the hypercube, then you accept only if the edge is cut, right? And therefore, the probability that this test accepts is precisely equal to the fraction of the edges which are cut by this cut, which is the Boolean function. Okay, so noise instability, it's same as the size of the cut. Okay, and this is why we want to study, right? We want to study size of the cut. So this is the dictatorship test, so as any test, we need this test to somehow distinguish dictatorship functions from functions which are far from dictators, right? So we want to study the acceptance probability of this test on dictators versus far from dictators. Now, clearly, if a function is indeed a dictatorship function, we know that the test accepts with probability, right? It's really 1 minus epsilon. If you think of rho as 1 minus 2 epsilon, right? Epsilon is the probability of flipping. So if you express in terms of rho, it's just 1 minus rho over 2. Again, just trust me on this. I know that all these little things you actually need to go back and check for yourself, right? But right, we are in this great hurry, so just trust me on this. The stability of dictator is just 1 minus rho over 2, which is great. On the other hand, in the soundness case, you want to show that if a function is far from dictator, meaning if all influences are small, then the probability of acceptance is low. Okay, low up to some threshold. But usually it's convenient to take the contrapositive, and the contrapositive would be if the acceptance probability is little beyond a certain threshold, and the threshold here being 1 over pi cos inverse rho. So if it's epsilon more than the threshold, this epsilon is unfortunately different from when we said rho equals 1 minus 2 epsilon. That's a different one. So henceforth, epsilon will be this small additive error which will occur everywhere. Okay, so if the acceptance probability is slightly more than 1 over pi cos inverse rho, then there is an influential coordinate. Okay, so that's the soundness conclusion. And in fact, there is a coordinate whose degree k influence is at least delta. And this soundness conclusion actually is exactly the theorem number 3, which I recommended that you keep it aside just to take a quick look. Okay, so now I will just give you like 1 minute, to just stare at that statement of that theorem and just see that it's the same. Okay? Because the theorem was saying that if you take a function whose all influences are small, then the stability was, I guess, at least something. I don't know if I wrote stability or 1 minus the stability, which would be the unstability. So there is this tricky game of switching between stability and 1 minus the stability, which would be the unstability. But if you keep writing everything carefully, everything that I'm writing down is correct. Though I admit that if you are seeing it for the first time, it might be a bit too much to keep track of all these small minute details. In any case, this conclusion here, that if the test accepts with probability marginally more than 1 over pi cos inverse rho, then there must be an influential coordinate. Okay? This is exactly theorem number 3. And okay, and then this describes this dictatorship as predicate. Okay, now let's move on. Okay, so now the unique games conjecture, right? So unique games conjecture, it simply states that the label cover problem that we already came across in the last lecture is indeed hard, even in a very, very special case. Okay, so just to recall, what was label cover instance? You had an underlying bipartite graph G. You had a set of labels, little n and little m, for the left hand side and for the right hand side. And little m was thought of as, typically larger than little n. And then you had these projection maps, pies, for the edges VW, which described this constraint that the label of W must map to the label of V according to this projection map pi. Now, such an instance is called a unique instance. So unique is just a qualifier, right? If it's a unique instance, if in fact m equals n, and moreover, all these projection maps pi. Now pi is simply maps integers 1 through n to integers 1 through n, because m and n are the same. Then all these maps are bijections or 1-to-1 maps or permutations, whatever your favorite word. Okay, so it's an extremely special type of label cover instance, and that's all a unique game is. Okay, right. Yeah, but now label cover, we know it's hard, as we saw last time. But once you specialize this up to this level of specificity, we don't know whether this problem remains hard or not. And that's exactly the unique games conjecture. So it says that the problem still remains hard. But you necessarily have to settle for loss of perfect completeness. Okay? So it says that for every arbitrarily small eta and delta, there is a large enough constant n. N is the number of labels, little n. This will also be the dimension of the hypercubes when you do the reduction, right? Such that given a label cover instance L, it's NP hard to tell whether the optimum is close to 1 or is close to 0, meaning either there is labeling which satisfies almost all edges versus no labeling satisfy more than a tiny delta fraction. Okay, so this is the unique games conjecture. And now the reduction to max cut. So what we want to do is we want to take this instance of unique games and construct the instance of max cut, or it is more naturally viewed as a PCP. And it's the same trick as the last time. So now I'm going to switch to the PCP way of saying things, right? There will be proofs and tests, okay? So just like last time, the trick is the same. As a PCP, instead of asking the prover or the adversary to...
Yeah. Subhash, there is a question in the chat. Why is it called unique games conjecture? Why
right. Okay, very good. So first of all, unique, I guess you would agree that for every label to vertex W, there is a unique label to vertex V for which the constraint would be satisfied, and vice versa, right? Because these pies are just permutations or bijections. So the word unique is fine. Now, why it is called a game, that's a bit I wouldn't say unfortunate, but historically all these things came from study of interactive proofs in cryptography, right? That's even what led to actually the PCP theorem. And there, these were called multi-prover games, okay? Because in cryptography, there are always these players, and they are playing games with each other all the time. There are, right? So this is how the term game percolated through, and therefore now these are called unique games, which I guess, yeah, I wouldn't say it's unfortunate choice of terms, but it's certainly a bit confusing choice of terms because there are many different types of games. Yeah. Right.
Okay. Thank you.
Okay, so I will continue. So now we want to construct PCP, and just like the last time, instead of now asking the prover or the adversary to give us an actual labeling, we now ask the prover or adversary to give us a labeling in the encoded form. Okay, and the encoding is again the same. It's this long code encoding and or the dictatorship encoding. So let's say, suppose fix our text W. Here you are asking for a label which is an integer from 1 through n. So instead of giving me that integer or index, let's say j, from 1 through n, give me the long code of that index j, which will be simply the dictatorship function of the coordinate j, right? So you make these new demands that for vertices v and w on either side, instead of the label itself, now we have these huge strings, right? Strings of length 2 to the n, which are supposed to be truth tables of Boolean functions, okay? And for each v or w, these functions are now, say, f sub v or f sub w. These are functions on n-dimensional cubes, and these are supposed to be the dictatorship functions, right, of the coordinate, which is supposed to be the label. Okay. Now, okay, so this is what the proof is supposed to be, and here is how you might want to now. We already got the dictatorship test, right? Which on a single Boolean function, it takes a pair of inputs x and y and checks whether f of x is different from f of y. But now we have one function on left hand side and one function on the right hand side. But then there is a constraint pi between the two sets of labels, but the sets of labels are simply the sets of coordinates, right? And in fact, pi is a permutation, so you might as well think of it as really an identity map, okay? So what you really are trying to check is that the function f sub v and f sub w on the two sides, they are the same function, and moreover, they are a dictatorship function. So this is really all you are trying to check. And therefore, the test, which was f of x different from f of y, you could use the same test, except that the input x will be from the left side function, and the input y will be from the right side function. And this is how you would naturally try to construct the PCP from the dictatorship test, right? So just to recall, the dictatorship test is on a single function, and now we sort of extended it to two functions just by reading one bit from this side, the other bit from the other side. Okay, and this would be perfectly fine first attempt at the reduction. This would be your PCP, except that it suffers from a rather fatal flaw. Because when you think of it as instance of max cut, what it amounts to saying is these functions become actual hypercubes, and these tests between pairs xy, they become edges across the hypercubes. Okay, so if you look at the graph which is constructed like this, you get hypercubes on left, hypercubes on right, and edges going across left side hypercubes to the right side hypercubes. Okay, so this is how your graph looks like. But then this graph is bipartite, clearly, right? Because all the edges go from left to right, and you cannot have a max cut problem, which is a hard instance and a bipartite graph. Because in the bipartite graph, you just cut through the middle, and that is already the max cut. So the problem cannot be hard on bipartite instances. Okay, so, and this is really a fatal flaw in this reduction. But turns out this is not as fatal as it sounds. There is an easy fix. And this fix is like one of those, so-called tricks of the trade, which is if you are in the trade, these are all really minor tricks. On the other hand, if you're outside the trade, somehow these sound like more clever, right? But this is just one of those tricks of the trade. So this is an easy fix. So what you do is, so this is label cover. So there is a vertex V on the left. So instead of checking some constraint between a vertex V on left and a vertex W on right, instead fix V and pick two of its neighbors, W and W prime. Okay, and now we know that the labels of V and W, they are related by this permutation pi, and label of V and W prime, they are related by this another permutation called pi prime, and therefore you can take the composition of these two permutations, and therefore label of W and label of W prime, they must also be related according to a permutation, which is composition of the two permutations, right? And therefore you might as well carry out a test between the long code of W and the long code for W prime, right? And then if you view it as a graph, what is going to happen is the entire left-hand side, it will just disappear, but it's there, but it's only virtually present, okay? But the actual graph itself will only consist of copies of the hypercubes only on the right-hand side, and there will be edges going across some pairs of hypercubes, okay? And then you will be saved from this fatal flaw of ending up with a bipartite graph. Okay, so I hope at least that was somewhat clear, right? And then this is the PCP, and that's it. Okay, so the PCP is simply pick a vertex V from left, two of the random neighbors W and W prime, and carry out the test f of x different from f of y, but one bit from the function f sub w and the other bit from the function f sub w prime, right? And the entire left-hand side, which are the vertices V of the label cover or unique games problem, it sort of stays virtual in the background. Right. So yeah, now so I sort of already described the construction, and in 10 minutes.
Sorry, there seems to be a question.
Sure.
Which I don't quite understand. So maybe Banerjee could actually ask it. And
okay.
Yeah, so is it the same, the bipartite unique game conjecture, like the two term I heard? So one is this linear, so unique game conjecture. So
right. Yeah, I mean, so if you have tried to read literature independently of this course, you will see that the unique games conjecture itself has a bipartite version and a non-bipartite version, but they are just both equivalent to each other, so it's not much of an issue.
okay, thank you.
Right. Okay. Right. So yeah. So what I plan to do is we have 10 minutes. So let's see however further we can go, and if we need to continue next time, I can quickly spend like first 5-10 minutes next time. Right. So okay. So now we are actually doing the analysis of the reduction. Now, for the sake of analysis, or even for the sake of this construction, we have all these maps pi's, right, which are supposed to be permutations. It's conceptually just cleaner and easier just to think of these as identity maps, identity permutations. Okay. Now, of course, the unique games problem, it will not remain hard if all the permutations are identity. Okay. So you cannot really assume that they are identity, but you can keep track of these maps in your mind, right? Mentally speaking. Okay. And everything will just work out essentially in the same manner. Okay. So just keep track of these permutations mentally, and just assume them as identity maps, just for the sake of understanding or just the sake of presentation. Okay. It will just make things cleaner. Right. Okay. So this is a unique games problem, and as a PCP proof, we have this function called f sub w, right? N is the number of labels, and we have these functions f sub w, which are Boolean functions on n-dimensional hypercubes for every vertex w, but only on the right-hand side, right? Only the right-hand side survives. And this is supposed to be the long code or a dictatorship of the label of w, which is an index from integer 1 through n. Okay, and the PCP, as we described, it will pick one vertex v from left, two of its neighbors w and w prime at random, and then carry out the test f of x different from f of y, right between the code for w, which is the function f sub w, and the code f sub w prime for the vertex w prime. Okay, and x, y are of course row correlated inputs. And this is just this is same as the dictatorship test, right? Essentially, f of x is different from f of y. But of course, if you really want to keep track of these permutations, you have to keep writing their dependence. So everything, all the coordinates, they are permuted according to these permutations. But as I already recommended, just even ignore this for the sake of presentation. Okay. And now all we need to do is to make sure that the completeness, you get it as you want, and the soundness you get as you want. Okay. So let's worry about the completeness. That's the easy part. So in the completeness part, you get to assume that the label cover instance or the unique games instance has a labeling which satisfies essentially all the edges or constraints. So just take that labeling, encode everything using the long code or the dictatorship test, dictatorship code, and everything is going to be fine. So when you pick a random vertex v and random neighbors w and w prime, the edge vw and edge vw prime, each of them, it will be satisfied with probability 1 minus eta, right? Because you satisfy 1 minus eta fraction of the edges. And therefore, with probability 1 minus 2 eta, both the edges get satisfied. Okay, meaning the label that you assign to v, the label that you assign to w and w prime, they are all exactly the same, and call that label I sub 0. I mean, up to these permutations, which you are keeping track in your mind. So up to these permutations, the labels are all the same. And then we use dictatorship functions. So both the functions f sub w prime, they are dictatorship of the same coordinate I sub 0. And therefore, and then you're just doing the test, the dictatorship test, and therefore, which will accept with probability 1 minus rho over 2. Right? This was the acceptance probability of the test if the function was indeed a dictator. Okay, and therefore the overall acceptance probability is this 1 minus rho over 2 times this 1 minus 2 times eta, which was the probability that you did satisfy the edge VW and edge VW prime. But eta is arbitrarily close to 1. So this is essentially 1 minus rho over 2. Okay. So you get this as you want. The completeness is 1 minus rho over 2. And the goal is to show the soundness, that is at most, say 1 over pi cos inverse rho plus some arbitrarily small additive epsilon. Okay. And once we do this, we are done, right? This is a reduction to max cut with the exact gap 1 minus rho over 2 and 1 over pi cos inverse rho. Okay, and we get the exact hardness result. Now, again, this is something I should have emphasized before, but let me do it now. Is at least when we did this around 2004, and the Gomans-Williamson algorithm came around 1992, right? So in 2004, it sort of looked like, you know, amazing accident that how come you get exactly the same expressions, right? 1 minus rho over 2 and 1 over pi cos inverse rho, and then the ratio of the two, both working from the hardness side and working from the algorithmic side, right? And then, right, and then you exactly match the approximation factor and the hardness factor. So that sounded like some sort of, I guess, accident. Yeah, but then over the next 10 to 15 years, we learned that, you know, there are no accidents in life. Everything, you know, has an explanation, this and that. And yeah, so now we have much better understanding of why this even happens, that you arrive at the same middle point, working from algorithmic side and from the hardness side. And turns out this happens not just for the max cut problem, but even as a purely formal phenomena for all problems which are called constraint satisfaction problems. Okay, and this is a result of Prasad Raghavendra, which is quite well known in this area. Okay. Yeah. So in any case, we want to show that if this test accepts with probability marginally more than 1 over pi cos inverse rho, then then we can arrive at a contradiction. And just like the last lecture, we will arrive at a contradiction by coming up with a labeling to the label cover or unique games instance, which satisfies a good fraction of its edges, right? And therefore, if you had a priori chosen the unique games instance to have sufficiently low soundness, then it would be a contradiction, right? So I hope this general scheme you remember from the last lecture. Right, so the goal is to come up with a labeling. And again, the labels are coordinates, right? Coordinates from 1 through n. So So we want to again do this decoding. So given a Boolean function, let's say for a function f sub w, we want to identify some coordinate j, right, as some sort of spatial coordinate which we will then assign to the vertex w as its label. And having said so much about Boolean functions and influences, now it's clear which coordinates you want to pick as labels. These will precisely be the coordinates which are influential for that function. And this is what we are going to do, that for every function f sub w, we will make a list of all coordinates that have influence delta on that function, and then pick one of those coordinates as label for the vertex w. Okay? And again, to emphasize, we want this list to be of bounded size. Okay, and that's why I'm going to use actually the low degree influences, degree k influences. And then since sum of all degree k influences is at most k, I mean, that's what I showed on this separate screen. This list is at most k over delta. Okay, so it's going to remain of the bounded size. And moreover, what I will have to show is if I had this vertex w and w prime, right, which are, of course, they came from a common neighbor v, then when I do this decoding, meaning I take influential coordinates, there is some coordinate j which is influential both for the function f sub w and for the function f sub w prime, right? And then if I pick one coordinate, let's even say at random from the respective lists, list decoding lists, then I will hit on the same j, exactly same j for both w and w prime, right? And that will amount to satisfying an edge or the constraint of the unigames. And this is how I will get my labeling. Yeah, so at least at a high level, this is similar to what we did right in the last lecture. And it's going to be a randomized labeling because for each w, the function f sub w could have a bounded list of influential coordinates. So you'll have to pick one from this bounded list. So therefore, it's a randomized labeling. Again, the list decoding has to be bounded list, which I emphasized multiple times. And then here you seem to be assigning labels only to w's and the w primes, which are the vertices on the right-hand side of the label cover or unigame. But what about the vertices v on the left-hand side? Okay, so that's actually in hindsight is a minor issue, but all these issues need to be handled, which is done in the next 3 or 4 slides. Okay, so what I could do is maybe yeah, maybe let me just go over this slide, and then we could do something quick in the next lecture, just in the first 5-7 minutes, or we could even altogether drop it. It's not such a big deal either way. Okay, so it turns out whatever I said so far, it's already enough, right, for any hardworking student to go home and just figure out the entire analysis. It's already enough. But if one were to do it on one's own, things could get a bit messy or ugly, just in terms of presentation. But turns out there is a rather neat way of doing it, just in terms of presentation. I'm not saying conceptually speaking. Just in terms of presentation, here is a neat way of doing. So what's the probability of acceptance? So right, again, as before, right is an expectation of an arithmetic expression. Okay? So you read these 2 bits, fwx and fw prime y, and you accepted if these were distinct. So, right, so you write down the expression 1 minus the product of the 2 bits divided by 2, right? So this is 1 or 0, depending on whether you accepted or not. And then you take the expectation over all the choices that you made, right? So write down all the choices. You chose the vertex v of the label cover from left-hand side, pick 2 neighbors w prime, and then you pick this pair of inputs x and y, which are correlated. So write down everything and take the expectation, and then slowly manipulate. So it's half minus half the expectation of this this thing. Now put the expectation over v, x, and y outside, and expectation over for fixed v, expectation over w prime inside. Right now, for fixed v, w and w prime are independent choices, right? So you can write it as expect the product of expectations. So expectation of fwx and expected value of fw prime y over the random choices of w and w prime, independent choices. Okay. Now, since w prime, they are identically distributed, right? So these two terms, they are really the same, actually, right? So here is a real trick, a nice trick. So what you could do is this fwx, these are different Boolean functions, right? One for every w. Now you can construct a new function, which is the average of all these functions, and call it f sub v of x. Okay. So for every fixed v, you go over all neighbors w of v and take the average of all functions fwx. Okay, and call this function fv of x. Okay, so it's some massive averaging of all functions for fixed v. Yeah, so and then what you see here is simply fv of x. Okay, and this one will simply be fv of y. And this will be the expression half minus half, expected value of f sub v of x, f sub v of y. But then if you look at what this expression is, it's simply expected value over v, the instability or 1 minus the stability of the function f sub v. Okay, and therefore you are able to express the probability of acceptance very nicely as essentially in terms of the stability or instability of these functions, which are functions involved in the analysis. So what I could do is, yeah, I could stop here and we will continue next time.
Okay, yes. So thank you, and I think it's a good idea to stop here. So thanks a lot for the nice lecture, and we shall continue with Subhash's lectures in 23 hours, and in half an hour, Cheyenne is giving his lecture under a different link. Okay, so
okay,
thanks.
All right. Bye-bye.
Bye-bye.